Okay, so today we are very fortunate to be joined by Vadim Indelman. So he is an associate professor at the Israel Institute of Technology, otherwise the Technion, in the Department of Aerospace Engineering, where he runs the Autonomous Navigation and Perception Lab. So his general work is about estimation, perception, and navigation for mobile autonomous robots, especially handling problems of significant, doing all this in the presence of significant uncertainty. He's done a lot of cool work in the past relating to factor graph inference, particularly concurrent localization and concurrent filtering and smoothing, which is super cool stuff for those of you who've taken mobile robotics. It's very much in the fast, efficient factor graph inference framework, so I'd encourage you to check some of that stuff out. More recently, his group has started to do a lot of very cool work in belief space planning, so especially problems relating to efficient, tractable inference in high-dimensional belief space problems, but with actual performance guarantees, which is pretty cool stuff. So yeah, so I'm excited to hear about this particular talk, and yeah, turn it over to Vadim.
Thanks, Dave, and thanks, Chris, Lawson, and Dave for organizing this visit in such a last-minute notice. So I'm going to talk today about online decision-making in partial observable domains. We all know the motivation for these things. We would like the agents to be smart, to perform advanced tasks that involve capabilities such as information gathering, active sensing, autonomous navigation, and so on. And just to set the scene, I'm going to provide some brief intro. So for doing these tasks, we need to do basically perception and probabilistic inference, basically understanding what is the environment that surrounds the agent, either on a geometric level, on semantic level, or both, and to understand probabilistically where the agent and other entities are. On top of that, we really would like to do decision-making under uncertainty for MDPs, basically requiring to decide autonomously what are the next actions to take. And so in this talk, I'm going to take the autonomy loop perspective, meaning we are going to do things trying to do things online. So we can envision this cycle that happens at some frequency in an online setting where the agent maintains a distribution over the state. The state is application dependent. Then we have the planning model that does the decision-making. The output will be the optimal policy or action sequence, depends if it's closed or open loop. Then the agent will perform the action, sorry for the typo here, perform the action, get new data from the environment, update the belief, and the process repeats itself at some frequency. Okay. A bit more kind of on the intro level. So we have this distribution of the state, given all the data that we have access to, actions, observations. We do not write explicitly, but it is also conditioned on the initial belief, prior belief, and also on the models that we assume to be given to us. So, but we do not write this explicitly here. So some examples, we can consider a manipulator that kind of tries to localize an object it has to grasp. So it has some different hypotheses where the object might be. Or in a high-dimensional setting, we have maybe a SLAM setting where the agent moves, the camera moves, and observe different elements of the environment. And we have to, at the same time, localize the agent and reconstruct the 3D structure of the environment. Depends on the representation that we take, of course. Now, in terms of planning, we formalize the problem as a POMDP problem with this tuple where we have the state, observation, action spaces, the models, the stochastic transition and the observation models, a general belief-dependent reward model, and initial belief that comes from the inference part. And so with this, we can define the value function as the conventional definition as the expected sum of future rewards, where L here is the planning horizon. Okay, just again on the intuition level for now. Here inside of this belief-dependent reward, we have future belief, this belief, which is the posterior distribution condition on data that we have access to at time k, the planning time, the action sequence or policy, and future observations that we do not have access to. So these are treated as random variables. Okay, so hence the expectation over these variables. And we can consider different reward functions just on a level of formulation. It can be state-dependent reward functions, such as distance, expected distance to goal. It can be a bit more complicated reward functions, such as information theoretic rewards, information gain, entropy, and so on. So to wrap up this first part, let's consider this toy example. We have the agent. It is located in this cell. Of course, it is not aware of this data. And so instead, it does not know where it is located. So it maintains a distribution of the states where each bar corresponds to the probability to be in the corresponding cell. So this is the posterior distribution in this, in this toy example. Now in planning, we will reason how the distribution will evolve into the future for different future actions and for different future observations along the planning horizon. Now, it's intractable to do exactly. And especially when we consider high-dimensional settings, it becomes even more computationally intractable. And still, we would like the agents to be able to perform tasks autonomously, safely in an online setting. So how can we do that? So this is kind of the scene, the background for this talk. And what I would like to do now is to cover 4 different directions. I will cover briefly the first 2, and we'll spend much of the time on the third direction here, in a bit about multi-agent setting. So we'll start with experience reuse. So if you consider POMDP planning, online POMDP planning in continuous domains, continuum, action, observation, and state spaces, then we basically construct some belief tree here. And the current POMDP solvers basically identify the best action. Let's say this is the blue action. The agent will perform this action, get an observation. And since we are in a continuous setting, there's no chance that this observation has been sampled before. So we will be here. The agent will be located here. This is belief at time, the next time step, k+1. And so existing approaches typically perform the next planning session from scratch. They disregard the previous tree and construct a new tree. And the question is that we ask here, can we somehow reuse the calculations that we made here, which are quite expensive? Can we somehow utilize these calculations to make the computation of the current planning session more efficient? So basically, we'd like to have some way to reuse calculations to estimate this Q function more efficiently. Just in terms of notations, we're going to use G here for return, which this is basically the expected sum, sorry, the sum of future rewards will be denoted as G by return. Okay. So what is the idea? Imagine that we have now the belief at time K, and this is the current time. And imagine that we have access to previous data from some previous planning sessions or previous data set, whatever. So these are the previous data in terms of belief trajectories for different actions. And we are now located here. So the idea is to somehow access these previous data from the current belief at some specific actions that we consider. And what we would like to do now is to reason what is the likelihood of getting this to here from that belief with these specific actions. So for instance, if we take just this lace of belief sequences, here it is again, then we can define, basically these are the same belief trajectory, up to the initial part. So we can basically formalize this in the formulation of multiple of importance sampling for now, just importance sample, and this is going to be the importance weight, which is basically the ratio of likelihoods of that specific part of the trajectory when we condition on this belief or on that belief, right? And so now, since we have this whole data set here, some data, we can do this for each and every one of those laces. And this is why we can formalize this as a multiple importance sampling estimator, which since each one comes for a different distribution. And so we can have an estimator, an MIS estimator of the Q function by utilizing the different laces we have, each one with the corresponding return, which has been already calculated. This is available to us, so we save basically calculations here. Okay. So this is how it looks like, and it turns out that we can simplify this calculation by this likelihood ratio by just noticing that this part is common. So what actually matters is the difference between this guy and that guy. So this is what we have here. So it's easier.
The notation is very small. Can you tell me what that theorem means in English?
Yeah, so English, okay, so instead of calculating this long thing, which corresponds to the entire belief sequence, so this ratio boils down to calculating the ratio between the likelihood of that specific belief, of reaching that belief from BK-AK versus from BIK-AIK, which was the father. This was, we originally got this from this guy, but we're trying to access it from some other belief. So this is what it tells us. Thanks. All right. So in terms of briefly results, you can look the details in the papers. So this was the original paper from ICRA 19 a while back that kind of conceived the concept for, this is specifically for ML observations, for maximum likelihood observations. So we have this active SLAM scenario, and we show that we can speed up significantly the process and get similar levels of accuracy of planning. And since then, this is taken from the recent paper. This is for non-parametric beliefs, where each belief is presented by a set of samples. And the agent has to reach to some goal while localizing itself from beacons. So you can see here that using this process, we get a speed up of 1.5 in this case, in this scenario at least, and getting the same levels of performance roughly. Okay, and yeah, so we have different ideas how to utilize this concept further. For instance, follow-up work tries to see when we construct the belief tree online, we sample actions. And the question is, can we somehow update the sampled action via its value gradients? So basically, if we sample this action, maybe we want to go update this sampled action to this action and that action by following the gradient. And following the gradient, we show in the paper, basically obeys, also utilizes this kind of formulation, or it builds upon this formulation actually. So I think it can be interesting in details in the paper. All right, I want to briefly discuss high beliefs, and then I want to really spend time on the third bullet. Okay, so I will do this briefly and then go to here. So there are at least two reasons why should we consider beliefs over continuous and discrete variables. Actually, there are much more, but I will discuss just two. The first one, that we have ambiguous environments. So we have to reason about different hypotheses. For instance, do we observe the left bicycle or the right bicycle at each time? And the number of hypotheses grows exponentially with time. The other reason is that we have viewpoint-dependent semantic observations, meaning if we observe the same object, let's say, from different viewpoints, the classifier will give us different distributions. So there's a dependency between geometry and classification. So I'll briefly discuss this a bit in more detail. So you can see here an example from a real car. You can see the type of the car from this dashboard. I imagine you can see what the car is. And you can see here that what we show here is very absurd results, right? Let me show it again. So the type of this vehicle and the pose of the vehicle dances and changes abruptly from one frame to another. And suddenly it's rotated, suddenly there's a person. And one of the reasons for this behavior is that typically nowadays geometry and semantics are considered independently, separately. And that is problematic in our opinion. In practice, when we have an object, it really depends what is the viewing angle, right? Or what is the viewpoint that we observe the object at? So from this viewpoint, we may think this is likely to be the cake. From that viewpoint, it may be also, hat maybe. So it really depends on the viewpoint. But the viewpoint is actually uncertain. So this is why we have this coupling. And we introduced this some time ago, a model that we call that tries to model this coupling between the observation that comes from the semantic classifier or whatever you want, and the actual class and the viewpoint of the agent, relative to the object. And so with this, we can now reason about hybrid beliefs, beliefs over continuous and discrete variables. And we can present it as, with structure, parallelographs, and so on. And with this perspective, because we exploit the coupling between semantics and geometry, we can no longer assume that classes and poses are independent. And we can no longer assume that classes of different objects are independent of each other. And there's a kind of coupling between all those variables now. And this is in contrast to many other approaches that do either pair frame classification or just do not consider this dependency. So consider the viewpoint to be independent for the semantic observations. So they do not model this aspect. All right, so so our recent work takes this concept into planning. So the question is, can we actually do prompt planning with hybrid semantic geometric beliefs? And interestingly, this actually allows us to define the notion of semantic risk awareness. Basically, the idea is that the safety aspects are actually class dependent. It is really important for us to know what is the class of the environment, of the object that we observe. So maybe if it is a human, then there will be some safety area that is large. And if it is something else, the safety area will be somehow different. And so this probability to be safe is actually conditioned on that hybrid belief. And then this raises the question, well, we have to reason about these, different hypotheses now of the classification, joint classification. And if you have many objects in the environment, and several and m number of classes, we have this exponential dependency here. So this raises some concerns. For instance, can we actually sample from this guy without pruning first? Not possible, actually, without being a bit more sophisticated here. And we have some recent paper that I will not show you the details of this paper. I just want to skip this part. But in the paper, we show how we can nevertheless sample from this distribution, from decay, without first pruning the classes, which was tricky to develop mathematically, because if you want to sample, you have to sample according to the weights, right? But the weights are not given because this is the number of hypotheses. So how can you do this? So I will skip this part, but just want to mention that to do that, we can explore the structure, this structure actually. When we condition on the poses, then classes of different objects become conditionally independent, and then you can exploit the structure. That is the gist of the paper. So I'll skip these results. You can look at them in the paper if you want. And now I want to proceed to the second part here, that's the association part. So obviously, many of you are familiar with this maybe. So on the level of intuition, you have the agent and there's some uncertainty here about its location. And let's assume that it took an observation like this, slider or something like this. And this observation maybe can be explained by, let's say, in this case, two places, right, because of symmetry. And so if we have basically, in this case, two hypotheses. If we consider, let's say, the first hypothesis, in this case, this is the correct hypothesis. This is a posterior distribution over the agent location condition on that specific hypothesis. So in this case, if the agent has to reach to the star mark, to the goal, it will indeed, plan its actions to that goal. That's fine. But If we consider an incorrect hypothesis, then this will be the posterior distribution over the agent. And it will think it is here somewhere, but in practice it is here. And so the planning part will guide it upwards to the goal, and it will go to some unsafe area. So that's the problem. And so in practice, we would like the agent to be able to identify autonomously. Well, in these situations, we have to gather more data. And the question is, how should the agent act to do that? That we have to gather more data, so to understand that the probability of certain hypothesis is high or low, and so on. The issue is that we have the number of such hypotheses grows exponentially with time. And so when we plan, if this is our belief tree that we construct, inside there is a hypothesis tree that is hidden actually. So to see that, if this is the root of the tree, let's assume there's only a single hypothesis at the beginning. At each sampled observation, let's say this one, we have some branching factor of possible data association hypothesis. So this is 2, then 4, 8, and so on. So we have hypothesis tree hidden inside the belief tree. And because of this exponential blow-up, we cannot really support explicit calculations of all hypotheses at some time, basically. So one idea is to somehow sample promising hypotheses. Instead of this, so sample some promising hypotheses. So this is that paper. But really what we are trying to understand, okay, so you somehow select a subset of this tree. And the question is, can we say something about what is the impact of this subset selection on the planning performance? Maybe this can go to catastrophic results and so on. And this brings me to the topic that I really want to focus on now, which we call simplification of POMDP problems with guarantees. So what is the idea? We want to accelerate, to speed up the decision-making problem by breaking it into easier problems, maybe computationally easier problems. And we want to provide formal guarantees by relating between the original and the simplified problems. But that's not enough. We want these guarantees in terms of bounds, we want them to be computationally cheaper than the original problem, meaning we want the complexity of this guy should be ideally the complexity of the simplified problem. Why? Because if we can actually evaluate this online, then we can develop adaptation mechanisms that evaluate this, see if the bounds are, if the performance guarantees are okay. If they are not okay, then we can adapt the simplification and reevaluate things. And so we can basically kind of trade off complexity with performance using this framework. So over the time, we developed different perspectives of this framework, and I want to discuss it now. So the first thing was to say that decision-making is actually really about sorting the actions, action preference, which action is better. We don't really care what is the value of the value function, of the objective function, typically. And so if we have, this is conceptual plot, on the x-axis, we have different actuals or policies. And on the y-axis, we have the original problem and some simplified variant of that problem. If we can somehow guarantee that the action preference is maintained, preserved, then the same optimal action will be calculated by definition. Okay? And if that problem is cheaper, then we get a cheaper, the same action at a cheaper cost. Of course, in practice, it is not that easy to guarantee that. In practice, we may need to calculate bounds over the complicated problem, the Q function in this case. And as I said before, we want these bounds to be cheaper computationally. So what is the idea again? So instead of calculating the Q function or the value function for the original problem, these dots here, which is expensive, we want to evaluate these bounds for different actions or policies. Now, if the bounds overlap, as in this drawing, then we cannot guarantee the same best action as will be obtained by doing these calculations. So in such a case, we'll need to tighten the bounds by adapting the simplification. So we like to go to this case where there's the best action can be clearly identified because there's no overlap. So we can, in this case, assuming the bounds are deterministic, meaning they hold with probability 1, we can declare that we identify the best action of the original problem. So that is the idea. So with this idea, we developed different perspectives that I'm going to go over now one by one. But the idea is the same in all of these perspectives. So the first work was about belief specification for the Gaussian case. So imagine we have a SLAM setting. We maintain a high-dimensional Gaussian information form, or a squared information form. And now we want to do information theoretic planning. We want to reduce uncertainty, and we choose entropy to be the reward function. Okay. So as you know, entropy of the Gaussian case involves this determinant of this information matrix, of the posterior information matrix at the future time. And the idea here was, can we somehow take the original information matrix, or the square root of information matrix, sparsify it, meaning throw away elements, then calculate the posterior information matrix, in the future, and then do the calculate the entropy then. And the question is, can we somehow guarantee, or can we say something about action preference here in between the two variants? Meaning one variant is the original information matrix, the other one is the simplified version, sparsification in this case. There's also a nice graphical model perspective here that this sparsification, although it is performed in the conditional, we go into product conditionals here, but if you go back to factor graphs and so on, this has a nice perspective that we sparsify. We change the topology of the graph here by, in this case, you have this illustration, changing some factors, and this factor is not the same as this one, and I think it's a nice perspective. All right, so in terms of results, we show, in this case in Gazebo, that we have the original square root information matrix. And we consider here two different possible specifications. For this one, we can guarantee that we have exactly the same action trend. This is guaranteed, and the speed up is significant. For this one, we cannot guarantee formally. Empirically, we show that it has a very good correlation. We have bounds, but this is empirical results that shows, good correlation with the original problem. But the speed up is more significant then because it's just linear. Okay. Another idea in this line is to consider the topology of the graph. And prior work by Kosusi et al. Showed that the topology of the graph is highly correlated to the estimation accuracy. And the question was at the time, can we somehow utilize this very nice observation that they made, develop cheaper belief planning approaches? And so the idea is to somehow come up with a topological metric that is only a function of the topology of the graph and not the content itself. And so what we show here is what is called the Voigtnomen entropy of a graph. And what we can see here, that this signature function is only a function of node degrees, basically, which is interesting because it is very cheap to calculate, and it supports incremental updates, very easy to update it incrementally. And what we show here, there's a very strong correlation between the original cost entropy and the Voigtnomen entropy here. Very nice correlation. So in the paper, we show also bounds and so on, but here you can see some results. Again, in the Gazebo simulator, in this case, we have different topologies here, the correlation in each case, and the speed up is very much significant. Some results and so on. We also did a variant over this approach, what we call focus case. The focus case means that we want to reduce uncertainty not over the entire system, all the variables, but just over some variables that we call the focus variables. So as motivation, we may want to reconstruct a specific area better. We may want to reason about obstacles. And it has been shown in this work and also in other works that the optimal actions or policies for the unfocused and focused cases can be completely different. So it is not actually the same optimal solution. So also here we have this is the original cost reward in this case. Entropy for the focus case can be casted in information form as such, where this is the original information matrix, L steps ahead. And this is the part that is unfocused, meaning the variables that are not part of the focus variables. Expensive to calculate, basically. So instead, we came up with these signatures that are topological signatures that exhibit very strong correlation with the original cost. Some of them come with guarantees, with bounds that we have in the paper, and the speed up is quite significant here. This is, for instance, measurement selection and active SLAM. It is a substantial speed up in performance. All right, moving on. Another perspective of this framework is in the context of non-parametric beliefs, in the context of POMDP solvers. These days, these solvers consider non-parametric beliefs that are represented by a set of samples. So you can conceptually think that at each time instant, the agent maintains a belief that is represented by samples. And in this case, the simplification is what happens if we take only a subset of the samples. So instead of 1,000, let's take just 10 samples. And the question is, what is the impact on planning performance again? So in this work, we develop bounds over information theoretic reward function, entropy. Since we are dealing with non-parametric beliefs, we considered a common entropy estimator. It's called the Bohr's estimator. And we developed bounds that are cheaper to evaluate than the original function, the original estimator. And so the idea is the same. When we construct the belief tree, instead of evaluating the reward function, we evaluate the bounds and we adapt them if needed, such that there's no overlap. And we show that there's quite a nice speed up with guaranteed SLAM performance. And we can also take this concept to in any time solver in the context of Monte Carlo research in CTS. Also here we have bounds. And here the modification that was required is that when we construct the tree, we have to reason about exploration. We have to do UCT style reasoning. And these bounds were used to bound the UCB term in the MCTS approaches. And so to guarantee the same action selection at the root, in this paper, we had to guarantee that the bounds do not overlap when we construct the tree. And so when they do overlap, we'll have to tighten them by revisiting certain parts of the tree and adapting the simplification. This adaptation, for instance, in the non-parametric case, can be taking more samples, and then the bounds will be tighter. All right. Another perspective is, again, hybrid beliefs that we discussed before. So as we saw before, the number of hypotheses grows exponentially with time. So we can somehow choose, a subset of hypotheses because we cannot really evaluate all the hypotheses after some time. And in the papers, we kind of develop bounds that allow us to bound the value function with respect to all the hypotheses that we cannot really do after some time with a tree that we construct in practice, which involves only a subset of the hypotheses, which we can do in an online setting. So we have some results. And so these bounds, this is one instance of these bounds. Again, this is a bound that bounds the difference between the full tree, considering all the, here the full tree corresponds to the full hypothesis tree. Consider all the hypotheses to a tree that considers just a subset of hypotheses. And this bound, what is important here, it looks scary, but what is important here is that it can be evaluated online because it is only a function of things that are inside of this guy. So we can evaluate this online and adapt the simplification if needed. Based on this idea, I'm now going to simplification of models in the POMDP tuple and of spaces. So based on this idea, we kind of try to see, okay, we can do this for the ambiguous hypothesis and the association part. Can we take it, generalize it to POMDPs, basically, general POMDPs? And for general POMDPs, considering a discrete setting this time, discrete spaces only for now. So current solvers come with some either asymptotic guarantees, some of them do not come with guarantees at all. And it turns out that we can provide deterministic guarantees using this concept. So let's see how. It's the same framework. We take the original problem, we consider some simplification that I will introduce in the next slide. And then we ask ourselves, what is the difference between the original and the simplified variant? The same setting. Okay, so a bit more in detail. If this is the original POMDP tuple, we now consider the setting where we simplify the state and observation spaces. We just take a subset of those. This subset can be history dependent, meaning can change from one part of the tree to another. So it is history dependent here. And we also define the corresponding models here as those, it will be the same model, the original model, when we consider a subset we took, and otherwise it is zero. So you can see here that it is an unnormalized distribution, not sum to one. But nevertheless, with this, we define a simplified value function using all those using this tuple. And what we show in the paper, in this paper, that we can bound the difference between the theoretical tree that we should have calculated and the simplified tree that we calculate in practice, for instance, by sampling. So the sampling process, basically, this is how we define those subsets. This is one instance that can just sample, and then this, whatever is sampled defines the subsets of the state and observation spaces. So in the paper, we show that the difference between the value function of this guy and this guy can be deterministically bounded, which is nice in my opinion, only for discrete spaces here, the deterministic bounds. It is nice because we can use these bounds in different ways. For instance, we can utilize these deterministic bounds to prune branches, something that is not possible in MCTS without that. We can use these bounds to stop the anytime solver, meaning to say that after some time, no reason to continue because we have this deterministic bound. Again, current state-of-the-art approaches in MCTS cannot do this because they are either accommodated by any asymptotic guarantees and maybe probabilistic guarantees, which cannot be used for stopping criteria. Okay. The next thing what we did in this line is to consider simplification of models. So kind of the motivation comes from visual planning. We have kind of complicated models, maybe learned models. And the question is, can we go to simpler, more compact models? And what is the impact of doing that on planning performance? Conceptually for now, imagine we have some complicated model, maybe GMM, maybe network, and we somehow consider a much simpler version. Let's say, for instead of GMM, we have just a Gaussian, for instance. And so and the question is, can we say something about the impact of doing this operation on planning performance? And in this paper, we show that considering continuous space at this time, we can bound the difference between the theoretical Q function that considers the original model, this is PZ, the original model, and the estimator of the Q function that considers the simplified model, and this is a particle belief MDP setting. So this is a theoretical belief, and this is a particle belief MDP setting. And we have this time, these are probabilistic guarantees. It is not deterministic, but nevertheless, I think it is an interesting result. Okay. Next in line was the work that said, okay, we simplified the models, but we didn't change the observation space. Why don't we try to alter also the observation space? So we can imagine now that instead of looking at the original observation space, we have some other observation space, maybe latent space, that maybe has lower dimensionality or something like this. And we can do this switch at selective parts in the belief tree. For instance, we can decide that in this part, we take the original observation space. In this part, we take a simplified version, an alternative space. And in the paper, we show, we kind of ask these questions, how can we decide what parts, when we construct the tree, how can we decide, should we take the original observation space or should we simplify and take the alternative observation space? What happens if the bounds overlap? So we have bounds also here. How can we take one topology here and move to another topology to tighten the bounds by saying that if we had here an alternative observation space, we want to go back to the original observation space. So details are in the paper about this. And I want one more thing to say about this part. We also considered, in the context of simplification of spaces, we now consider partitioning of a multivariate observation space. And here, this work explicitly considers entropy as the reward function. So what is the idea? So we can consider that the observation is high dimensional, has some dimensionality M. For instance, it can be because we have a raw sensor, some images, or maybe we have landmark observations. We have many, many landmarks. So this is the dimensionality of the observation. And this is a future observation in planning. So this is a random variable, basically, multivariate random variable. And so the idea now is to consider some partition, split it into different subsets, maybe two subsets. It can be a hierarchical partitioning part. And then once why is it interesting, right? So just to motivate this thing. So as a toy example, if you have an image with binary pixels, let's say 20 by 20 binary pixels, then this is the number of possibilities if we should consider all the possible observations. If we do the partitioning and we consider each partition separately on its own, then we reduce it drastically to this number. So this is motivation. So in the work, we develop bounds that, so we consider a conditional entropy, which corresponds to the expectation over entropy, because here X and also Z are random variables. And you can see here that first we can factorize it in terms of the two subsets that we consider. And there is this term that couples between the two subsets. And in the work, we develop bounds over this guy, where the bounds decouple between the two subsets. So you can see here, this is decoupled. So it is much more easier to calculate. And now we can take this also. So this is general, applies to continuous, to discrete settings, and so on. We can take this to the more practical setting now, considering again a Gaussian case, where we have some future factor graph, and we conceive that we will observe some landmarks and so on. So this is the Jacobian of this thing. So in prior work of ours, 17, 19, we developed very efficient ways how to calculate entropy by utilizing the matrix determinant lemma. Just for intuition, if you consider information gain, then this guy cancels, and we just are left with this guy. And for intuition, if M here is the dimensionality of the number of rows in Jacobian. So if M, number of rows, is much smaller than the dimensionality of the state, with many, many landmarks, then this will become much more easier to calculate. For instance, if we just observe a single landmark, this will be a scalar, right? So at the time, it was a very nice thing to do. And now, coming back to the partitioning, we now show that partitioning in the Gaussian case corresponds to just partitioning the Jacobi into two parts or more. And the bounds that I showed before manifest themselves in the Gaussian case as such. We have some details are not very important, but what is important to say that at each time we consider just each of the partitions separately. So this was one partition, this is another partition, this is another partition. We never consider the entire thing at once. And this is what brings the speed up. So when we consider some results, this is a simulation for now, we show speed up compared to the previous work of ours, and the same results in this case. And this is a real-time, a real experiment with visual input, where we show the bounds, and the blue part is the exact solution of the entropy. And also here we show speed up compared to our work and compared to ISIM2 methodologies. I will briefly mention that we have also quite a few works on extending this framework to risk-averse setting, where we reason how a simplification impacts the distribution over the return. And then conceptually for now, there's some distribution here. We consider some abstract simplification operator that maps this distribution to some other distribution. And now we, instead of taking the expectation, we can consider some other metric that we can envision, that is maybe risk-averse metric, such as C-bar or something like this. And the question again, can we develop guarantees for this kind of thing? And we have promising results in this direction. Along these lines, we also consider a constraint setting where we have the main objective, and we have a constraint that is also a function of the belief. And we have here two possible forms that we consider so far in these papers. One form is what we call cumulative constraint because of the summation. For instance, it can be used for in the context of information gain. So if we want to reason when should the agent explore? So the agent should explore when we can somehow guarantee that the information gain will be significant enough. If it is not significant, maybe the agent should not explore. Maybe it should do something else. So this is one motivation for this part. Here, we can also support safety aspects. In this case, it's going to be a multiplicative form. We want to be safe at each of the time instances. So both forms are specific instances of this more general formulation. So I have a few minutes now, so I want to talk about the multi-agent setting now. And this is actually the way I see it for now is an instance of this framework, actually, where we consider what happens if the agents have access to inconsistent beliefs. What does it mean, actually? So imagine that we have two agents or more. So if the agents are capable of exchanging data with each other, so each agent has access to the same data and the same, at least theoretical belief. And then each agent can, plan its own actions and solve the joint decision-making problem and decide what are the best actions. So let's say these are the two possible trajectories. But this required this exchange of information. And the question we ask here, what happens if we cannot share all the data? So the agents may be limited in their sharing capabilities. And then in such a case, the histories that are available to each of the agents are going to be different because they didn't share all the data. So graphically now, visually, we have some common part that was shared. And there are unique parts that is available to each of the agents only. So this part is available to agent R and not to R prime and vice versa. And in such a setting, when we look at the DEC-FOAM-DP problem, then each agent has its own belief. So although everything here in the context of collaborative setting, it is the same reward function, they have the same task, but the belief is different here. So this difference impacts at different places. It impacts us here, and it also impacts her here, the expectations taking respect to that belief. And this is, bad news, basically, because we can conceptually think that if there's no communication, then this may lead to lack of synchronization, can lead to collisions, or generate some, suboptimal performance, basically. And the question that we asked in these papers is, can we somehow guarantee a consistent joint action selection or coordination by different agents in the decentralized setting, despite the agents having inconsistent data? And if we cannot guarantee that, can we somehow develop self-triggering communication mechanisms such that the agents may identify what data should they communicate such that we can guarantee it after the communication? So I don't have time to really go over the details, but I want to mention the concept for now. The concept relies on the action consistency that we discussed before. Again, I remind that this concept tells us that decision-making is only about action preferences here. So if you have two different decision-making problems, if we can somehow guarantee the same action preference in both, we get the same action, the same best action. And so we are trying to utilize this concept now in the context of multi-agent setting. So what is the idea? So we want to guarantee a consistent multi-agent decision-making where each agent will reason about its own and other agents' action preferences. And to do that, they have to account for the missing information. So let's see an example. So we have three steps, basically. First step, the agent reasons about its own local data. Let's see this. So if this is the diagram, the Venn diagram that I showed before, the first agent, let's say agent R, makes a decision based on the data that is available to it, HR, basically. So in these two examples, let's say we have only two possible actions and only two possible observations, then agent R will calculate these two values. Second step, the agent R will think about the same step from the perspective of agent 2. But agent R does not have access to this data. So it will think about all the possible values that this guy can assume. In this, for example, just two possibilities. So these are the two squares here for each of the possible actions. And we check here, are these lines follow the same trend, the same preference? If not, we immediately know there's no guarantee on action consistency. Third step is that agent R reasons about the second step of agent R prime, meaning agent R knows that agent R prime will reason about agent R missing information. So basically here, agent R reasons about its own data that it knows that it is not available to the agent R prime. So these are these triangles. Again, we look for action preferences, if they are the same or not. So if we take everything combined, this is the combination. If we see that all the trends are the same, if all the preferences are the same here, then we can guarantee deterministically in this case. And if not, we can self-trigger communication. That is the concept. And based on this, we developed some theory, and we can go to, and so before that, we can show that in different simulations, we can reduce drastically the number of communications and get very good results, basically in terms of zero inconsistent decision makings. And in practice, the value function is going to be very similar to the full communication part. And based on this concept, we develop also generalizations. We can do now probabilistic reasoning, what is the probability of having a multi-agent, multi-robot action consistency as more data is accumulated, and so on. So the details are in these papers. All right, so just to wrap up what we discussed today, briefly discussed about experience reuse in POMDP planning. I discussed about POMDP planning with hybrid beliefs. I spent some time on the simplification framework of POMDPs with formal guarantees. We saw there's different variants of that framework. And lastly, we discussed multi-agent planning with inconsistent beliefs due to limited data sharing. With that, I want to conclude, and I want to acknowledge my group, postdocs, research scientists, students, of course, and funding resources. Thank you so much.